continue with point estimation. And remember we said that we would cover three main methods, at least for now. Method of moments, maximum likelihood and Bayes estimation. And so what is the setup? The setup is we have x1 to xn, on the density. And we're in the parametric setting. So theta is a parameter. Hello? Thanks. So we have a parameter, theta, and well, theta could be a scalar, it could be a vector. In fact, let's say it's a vector. Like k. So for example, in the normal case, it would be a vector like 2, right? Mu and sigma. So the way the method of moments works is to take, we have to find these k quantities. So let's take, the idea is very simple. Let's take k things that we can estimate very easily, and let's equate it to k things that we know should be true. And what I mean by that is, what we're going to do is, let's define mu1, which is, I should really write it mu1 of theta, which is just the expected value of x. This is a theoretical calculation we can do from the model. If I tell you the data are normal or gamma or beta, whatever, and I say find the mean of x, you can do it. But the answer, because it's going to be, what is this? When you do this, it's going to involve theta. So you're going to end up with some function of theta. So this is a theoretical quantity. But we can also compute, in some sense, a sample version of that. Let's call it M1. Sample average. What do we know about the sample average as n gets large? Yeah, by the law of large numbers, this converges in probability to this. And now we just do the same thing. We go to the second moment, which would be the expected value of x squared. Again, that depends on theta. And then we can compute the sample version of that. And we do that k times. And then what we do is we have these k things that depend on theta. And by the law of large numbers, they should be close to these k things, which we can compute from theta. So we equate them. And we end up with k equations and k unknowns. So now we equate and then when we solve for that, we get an estimate theta. Heuristically, that seems like it should give us a pretty good estimate of theta, because again, we know this should be close to this by the law of large numbers and so on. So let's just do an example. Let's suppose we have a normal, and just for fun, I'm calling the mean beta today instead of mu. Actually, the reason why I'm doing it, they're already using mu over there. So call it the mean beta and the variance sigma squared. So our two parameters are beta and sigma squared. So let's see how this works. What I do is I should get two equations and two unknowns. So how does this work? So I'm going to compute first sample moment and equate it to, and what's the expected value of x in this model? First moment? Beta, right? And now I'm going to compute the second moment, but I have to compute the theoretical second moment. But the expected value of x squared, remember, is the variance of x plus the mean of x squared. And this is sigma squared squared, and this is beta squared. So this gets set equal to this. And now I just solve these two equations of two unknowns, and you can see what it's going to be. Beta hat ends up being x bar, and if you do some rearranging, sigma hat ends up being, you have to do just a little bit of algebra here, this version of the sample variance. Of course, this is only going to work if you can solve these equations. If you ended up with horrible equations that you couldn't solve, this might not be so helpful. Fortunately, it's very often the case that we can solve these things. And what you can see about this is when you can solve the equations, it typically leads to very simple estimators.
For example, that estimator of variance is biased. Like you should put like.
Right. So that's a good question. So you may have seen other estimators of sigma squared that have n minus 1 here. But that has to do with bias and variance and stuff like that. So right now we're just defining the estimators. We haven't talked about the properties. So I haven't said these are good estimators. All I'm doing is giving you kind of an algorithm for deriving an estimator. Any other questions? All right. So let's do another example. Kind of an interesting example, and a little bit unusual. When we talk about, usually when we talk about coin flipping, like Bernoullis or binomials, we think of the number of tosses as fixed. So when we talk about, let's say a binomial, n is usually thought of as a fixed thing, and p, the probability of success, is the unknown parameter. But there are cases when n is also unknown. And you could say, can you estimate that parameter? Well, not from 1, but you could estimate it if you have repetition. So let me explain. This is example 2 on model page 2. Suppose I have n observations, but each observation is itself not a Bernoulli, but a binomial. So binomial with k and p. And both of these are unknown. So here's the way to think about this is somebody flips a coin k times, and all they tell you is I got this many heads. You don't know the probability or the number of times they tossed it. Then they repeat the experiment a second time, and you repeat it n times. And you're supposed to estimate k and p. So when does this come up? This actually comes up in certain ecological studies, where they'll fly a plane over a certain region, and they're trying to see how many gazelles there are, or something like this, let's say. And they'll count, okay, today we counted there was 53 gazelles. But then they fly over tomorrow and they repeat the experiment. But the thing is, they don't see all the gazelles, right? They only see the ones that happen to be wandering around this area. So you can think about it as there's a success or a failure. Success is if the gazelle shows up, and failure if it doesn't show up. And there's some probability that every gazelle will show up in the picture. But what you'd like to estimate is the size of the herd, k. And so in this case, the parameter k is actually a parameter of interest. It's an unknown parameter if you actually want to estimate. So let's work out the method of moments estimator. The first sample moment is this, and well, what's the mean of a binomial? It's k times p. And then the second moment, second sample moment is this. And now, again, we'll do the same thing. It's the variance, which is k p 1 minus p plus the mean squared. So once again, two equations, two unknowns. You can solve these, and what you end up getting is p hat is x bar over k. Remember, there's k different binomials this time. And interestingly, k hat turns out to be x bar squared over x bar . This is just from algebra. But let's look at this estimator. So this gets to the question again, is it a good estimator? We haven't talked about that yet. In fact, we'll see that in some circumstances the method of moments is a good estimator, sometimes it isn't. This one could have problems. The variance can be very large. And there's another problem, which is if you look at this, it's possible this could be negative. And that would be a pretty bad estimator, the size of the herd, negative herd. So we're not claiming these are always good estimators, but right now, it's just a method for getting estimators, and we're really separating this notion of coming up with a method to derive estimators, and then deciding how we can evaluate whether the estimator is good or not. Yes?
So there you have P hat equals X bar over K, yeah?
Oh, I'm sorry, that's actually a typo. I think that should be probably, that's a good question. I think, what should that be? Should that be over, I think, yeah, I was gonna say K hat. Yes, that's right, K hat. That should be a K hat. Otherwise, you can't have an estimator that involves unknown parameters to be a very good estimator. So that's a typo, thank you. Let's fix that here. So it's good exercise to take other models like the uniform, beta distributions, any distribution you can think of, and work out what the method of moments estimator is. And again, sometimes you can work it out very explicitly, sometimes it can be difficult. I mentioned in the last class that there's a lot of effort these days into dealing with some high-dimensional models like mixtures of Gaussians. That's a model we'll talk about at some point. Using the method of moments, and there it's tricky. It takes some work to figure out what the method of moments estimator is, but it can often be a very useful estimator. So that's method one, but it's not the most common estimator. I would say the most popular estimator is the maximum likelihood estimator. If you pick up an issue of Science or Nature and look at the scientific articles in there, they're filled with maximum likelihood estimators. They're all over. Every biology, physics, everywhere you look, there are maximum likelihood estimators. Maximum likelihood, at least in its modern form, was invented by Sir Ronald Fisher, who I mentioned in the previous class. He invented most of, or quite a bit of modern statistical theory. And although they appeared much before that, but it was Fisher who really systematized it. And the estimator is very simple in principle. We compute the likelihood function. Remember the likelihood function? Just this, or in the IID case, just this, where we regard this as a function of theta. So let's draw a picture. Here's theta. Maybe it looks like this, who knows? And it's just as the name implies, it's the place where this is maximized. So that's theta. So theta hat is the point that maximizes and there's some notation for that, just to write argmax. Argmax just means the place where this function is maximized. So again, I'm writing it just as theta hat, but really, it depends on the likelihood function. The likelihood function depends on all the data. So remember, this is actually a function of all the data. And right away, let me say that people very rarely maximize the likelihood. Instead, they usually maximize the log likelihood. It's usually numerically easier to maximize the log likelihood. Remember, the log likelihood is just the log of all theta. Because log is a monotone function, when I take the log, the shape of the function changes, but the maximum occurs in the same place. That doesn't change the location of the maximum. Like the function will now have a different shape, but if the likelihood of this is bigger than the likelihood of this, then the log likelihood of this is bigger than the log likelihood of this. That doesn't change the location of the maximum. So usually people actually focus on maximizing the log likelihood. So this is the MLE. This is by far the most common and famous estimator. And when we talk about properties of estimators, we'll see there's good reasons why it's the most common estimator, because there are certain cases in which it's an optimal estimator. Not always, but under certain conditions it's optimal. Now, how do you actually find it? So if you have, if you're lucky and you have a nice was that concave? I was a concave function with a unique interior maximum in the interior. You can just, by calculus, say, well, I can solve this equation, right? The derivative of, well, that will define the estimator. Or more generally, I guess if you had a vector of parameters, you'd have a system of equations to solve. The derivative with respect to K1. You would take all partial derivatives, set them equal to 0, and solve to get theta hat. But this, remember that taking the derivative and setting it equal to 0 doesn't necessarily give you the maximum, right? You have to verify that it's concave there and so on. But assuming they're a sufficiently nice function, it's common to get the MLE just by taking the derivative and setting it equal to 0. There's lots of cases, though, where the MLE has to be found numerically. Now, obviously, I don't tend to do those on the board because there's nothing I can do to find it numerically. So, beware that in textbooks and so on, and in the classroom, we tend to do easier problems where we can just find the solution analytically. But in real life, people fit some pretty complicated models with lots of parameters in them, and typically you're going to have to do some sort of numerical method. There's a million numerical methods. The class right before ours that takes place right here is a course on optimization, so it's all about methods for finding maxima and minima functions and so on. So that's a whole big topic in and of itself. I'm not going to talk about the numerical things about finding the maximum likelihood estimator. We'll just always assume for this class that somehow you can find the maximizer. We're interested here in the statistical properties of the maximizer. So is the definition of the estimator clear? Any questions? Let's do a couple of examples. So, let's start with the Bernoulli. So we flip the coin n times. We're back to the case where n is known, and we're only looking at a single coin. So these are individual coin tosses. And with the p, we want to estimate p. So, all right, the likelihood is the product of p to the xi, 1 minus p to the 1 minus xi, either success or failure, which we can write as p to the s minus p to the n minus s. The s here just means the sum, roll over heads. And so the log likelihood is s log p plus 1 minus s log 1 minus p. If you plot the likelihood function, of course it lives between 0 and 1. And it turns out it looks something like, let's say that. And you can verify that it has a unique interior maximizer. And you can find the maximum just by setting the derivative equal to 0. That's an easy exercise. If you do that, make L prime equal to 0, you'll get x bar. Sort of what you'd intuitively expect. In this case, the method of moments estimator and the MLE are the same. That happens sometimes, but not always. Okay. So that one was pretty easy. Let's do the Gaussian. So let's say, let's do Gaussian. And one of the things we did was we rewrote the log likelihood. Remember, we did some algebra to rewrite it in a more convenient form, and it looked like this. It was e to the minus n star q squared q sigma squared e to the sum x minus x bar squared over q sigma squared. So first of all, you can see, if I try to take the derivative of this with respect to mu sigma and set it equal to 0, it's actually a mess. But when you do it on the log scale, it's very easy. So typically, again, people use the log. So I'll leave this as an exercise. If you take the derivative of this with respect to mu, set it equal to 0, and the derivative, let's say, with respect to sigma, set it equal to 0. So let's say sigma squared. So that is the parameter. You will get mu hat is x bar, and sigma hat squared is 1 over n. Which again, in this case, happens to be, you can check exactly the same, I guess we just did it, is the same as the method of moments estimate. But let's do one where it's not the same as the method of moments. This is one of the last examples we talked about one day, where I have a uniform between 0 and theta. And we worked out the likelihood between 0 and theta less than the max, and 1 over theta being theta bigger than the max. So the likelihood looks like this. I find the maximum data point. The likelihood is 0 up to this point, and then it looks like this. So here's an example. First of all, you can't use calculus in the sense that setting the derivative equal to 0 won't help you because it's a boundary solution. You can see where the maximum is, right? You can directly see that the maximum occurs here. So theta hat is xn. That is, it's the maximum. Let's actually figure out what the method of moments estimator is. What's the mean of x when we draw from a uniform? 8 over 2. So, to get the method of moments, we would set theta over 2 equals to x bar, and that defines our estimator, theta hat equals to 2x bar. So we have two very different estimators there. And so the thing you keep in the back of your mind is now we have two different estimators, they're very different in this case. How do we decide which one's better? That's the question we want to address here. It's easy to dream up estimators. It's another issue to talk about which one's better. Now, maximum likelihood is a very important property. But to explain that property, I first need to introduce a little bit more terminology, which is something called the profile likelihood. So suppose we have several parameters. Let me just say, in general, let's suppose I have a parameter. That's the Greek letter eta. I can't write it very well. And this is the Greek letter xi, I think. Should have picked ones I could draw better. And you know, the MLE is just, again, it's just the thing, it's just the value of theta that maximizes this. So we can find theta hat. But that theta hat I can write, of course, as its component. So think of the normal case. I had mu hat and sigma hat. And that's the MLE. But sometimes people like to think about the likelihood focusing on one parameter at a time. Let's say I want to just focus on that parameter eta. Or in the normal model, I just want to talk about the likelihood of mu. Is it possible to talk about the likelihood of one parameter? So the way people usually do that is they define a profile likelihood, which just means you maximize the likelihood. So I'm going to write it like this, L of eta. Just take the maximum over the other parameter. It's called profile because it's like I'm looking at this surface and then holding it up to and there's a shadow there, it's forming a profile. I'm just looking at the shape of the likelihood over this parameter, maximizing over the other parameter. This would be a way, if you wanted to visually display the information somehow about one particular parameter at a time, you could look at this. Now you can maximize this to get an MLE just for this. But that's exactly the same as this, right? Because if I think about some function I'm maximizing here, let's say I find the maximizer here, but I could, what am I doing when I'm finding the profile liquid? I'm finding the maximum along each stripe. And then I'm maximizing that. Well, of course, that's going to give me the same overall maximizer. So whether you find the overall maximizer or whether you find the profile liquid first and then maximize that, you're going to get the same MLE. And, yeah.
Likelihood function is always convex function.
Sorry?
Likelihood function is always convex.
No, the likelihood is not always, the likelihood could be any shape. It's not convex, concave. No, it could be anything. Life would be very easy if likelihoods were always concave. Save a lot of numerical problems.
If you do this approach, are there cases where you could end up kind of chicken and egg problem where one of the parameters is dependent on the other and the other is dependent on
Well,
the first one?
this is not, like I said, you're going to get the same answer. This is just a different way to get to that particular estimator. And I'm not even suggesting you should do this. It's only because I'm about to show you a property of the likelihood which wouldn't have made sense if I didn't show you this first. So really, the profile likelihood used to play a big role in statistics at some point, but these days it's really not that important. It's really, I'm really just showing you this so I can explain the next concept. You should really just focus on the whole likelihood is the main thing. But you'll always get the same answer if you did it this way. I think you're asking what if I now found xi-hat, but you would just get the same thing because it would still be the same overall maximizer. But the reason why I want to mention this is because, maybe I shouldn't even spend so much time on that, because I want to tell you that the MLE has a very nice property which is called equivariance, which makes it very convenient. What do I mean by equivariance? Suppose I'm interested in some function. So here's a parameter theta. Maybe I'm interested in a function of theta, like e to the theta, or log of theta. What's the MLE of that? And it's easy to see that, let's start calling this here. The MLE of this is just this. Why is that? Because the value that maximizes if I just relabel the point, so here's my likelihood. Let's say this is theta, this is L of theta, this is theta half. Suppose now, no one says I have to index, let's say these are normals, okay, normal theta. I could look at, let's call theta to be equal to e to the theta, right? There's nothing to stop me from indexing these distributions by e to the theta instead of theta. It's just an indexing variable. It's just telling us which parameter value corresponds to which thing. So in other words, I could eat it down here by applying some mapping. That's just a mapping. It's just changing the scale. It's like changing from Fahrenheit to centigrade or something like that. But when I compute the likelihood, that's still this value and this value here. This value of eta corresponds to some value of theta. And the likelihood is just the density function when I use this value. And so, if I look at the likelihood function, the product of the densities of this value, compare it to this, that's the same as looking at the likelihood and comparing it to this. So, if the likelihood here is bigger than this here, then even if I do it on a different scale, it still has the property that the likelihood at this point is bigger than the likelihood at this point. It's simply a relabeling of the points.
Doesn't it have to be monotonically?
It does not have to be monotonic.
You can do like inversions.
So that's where this is, which is, suppose it wasn't one-to-one. Suppose there was two values of theta that mapped to the same guy, this would still apply as long as we interpret this to mean the maximum of the profile likelihood. But what happened now is instead of there being, for a given eta, so what he's asking is, for a given eta, suppose there wasn't one theta. Suppose there was two different thetas that corresponded to that. What do I mean by the maximizer? Well, now there's actually, it's just like this situation. There's a profile likelihood, the maximum of likelihood over these two values. That's why I introduced that. And by the same argument, the same thing holds. That the thing that maximizes this value, you get by first maximizing this and applying the function. It's really almost a matter of definition. Let me give you an example though. This will make much more sense. This will make much more sense if I give you an example. So let's go back to our coin flipping example. We saw that P hat was x bar. So that was easy. Until you give this, say you're working with an epidemiologist, you say, I just estimated the probability of the fraction of people who have some disease in some city. But your epidemiologist says, I don't care about P. We epidemiologists, we work with something called log odds. They use log and P over 1 minus 2. It's just a more meaningful scale for them. That's just some transformation of P. He says, I want the MLE of this. Now, if you had to somehow redo the whole problem and figure out how am I going to find an estimator for this function, you have a lot of work to do. But for maximum likelihood, all you have to do is this. This is the equivariance property. In other words, if you took the original likelihood and re-expressed it in terms of psi, this new parameter, just substitute everywhere. You can solve here for P. P is e to the psi over 1 plus e to the psi. You can just, everywhere in your original likelihood, you can just replace the p's with these things, and you have a function of psi, and you can maximize it. But you can check very easily, you're just going to get back this. So you can check this yourself and verify that that's true. But the point is, you don't have to do it. If you're interested in a function of the parameter, you just first do the MLE of that and then apply the function. It's a nice property now. It's not a property shared by, like someone mentioned unbiased estimators, so we'll talk about those later. I haven't explained what that is, but if you have an unbiased estimator P, it doesn't mean you have an unbiased estimator automatically. So, but for maximum likelihood, you instantly have not just an estimator of the parameter, but any function of that parameter. That's called equivariance of the MLE. That's a very, very handy thing. Let me give you another example. Suppose we're estimating this. We saw the MLE mu hat x bar, and sigma hat squared is this. Now your friend says, oh no, I didn't want to estimate sigma squared. I wanted to estimate sigma, which is the square root of that. No problem. Sigma hat's just the square root of sigma squared, so you just take the square root. Or maybe your friend says, actually, I forgot to tell you, I really wanted to estimate the coefficient of variation, which is mu over sigma. Mu over sigma or sigma over mu, one of the two. Anyway, that's some function of mu and sigma. No problem. You know what the MLE is. You just plug in the estimator of that, and you have over sigma hat. You're done. So that's a really nice property of MLEs that's not shared by some other estimators. Very convenient. All right. So now we've done method of moments, we've done maximum likelihood. Question?
Could you just repeat the argument when the function is not 1, 1?
I'm sorry?
Could you repeat the argument for what happens when the function is not 1, 1?
If it's not 1 to 1, so let's say here's theta, here's theta. Suppose this theta and this theta map to the same value. What do I mean? And suppose this is some other value. What do I even mean by the MLE? Technically what I mean is there's two values. So I'm going to define the likelihood here. It's just like in that other situation over there where they had extra parameters. I'm going to define the likelihood to be the profile of it, that is the maximum of these two values. And you can see that the map, if this, now if the white piece here is bigger than this, then it's also true that one of these must have been bigger than this, and hence the maximum is bigger than that. So it wouldn't matter whether I did it on the original scale theta or just compute the MLE and then apply the function. You can write, it's not a bad exercise to write that down, make that precise. It's probably easier to think about it in the one-to-one case, but it's true more generally. To some degree, it's a matter of definition. In other words, defining the likelihood here in that case to be the maximum of all of these two values. Any other questions? All right, so we're going to come back to, again, the properties of this guy later. I want to keep going through the definitions of the estimators before we talk about the properties. And now we have to get to our third one, which is the Bayes estimator. Now, for those of you who are familiar with Bayesian inference, don't get confused. The Bayes estimator is not Bayesian inference. Those of you who don't know what Bayesian inference is, you can just ignore that last sentence. For now. For now, this is just another algorithm to compute an estimator. Right, so here's the algorithm. The algorithm is, we have this parameter theta, which is a fixed but unknown thing, but we're going to temporarily pretend that theta is a random variable. We're going to treat it as if it's a random variable, which means I can put a distribution on it. So I'm going to put a distribution, T of theta, on theta. This is called a prior distribution. So again, we're just temporarily treating theta as if it's a random variable, even though it's not a random variable. Why are we doing this? Well, because now we can do the following thing. I have x1 to xn, and I've always been writing it like this, to indicate that these are random variables, and this is a parameter. But now, since we're treating theta as a random variable, I can actually think of this as the distribution of x1 to xn given theta. Okay? And I also have a prior distribution, which I haven't said where we're getting yet, but we're going to put some distribution. So now I have the distribution of x given theta times the distribution of theta, so that automatically defines the joint distribution, x1 to xn, and theta, right? That's just the basic probability of x given y times the probability of y is the probability of x. So now I seem to have this sort of quasi-distribution for all of these things. That means I can now also do conditioning the other way. I can now find the distribution of theta given this. So I'm going to find what's called the posterior distribution. The distribution of theta given all the other x's. And we know from Bayes' theorem, well, let's find out what that is. That's the distribution of x1 xn over theta. Over e of x. That's just, again, the same rule. Probably theta given x is the probability of theta and x over the probability of x. Now I'm going to rewrite this the other way. X given theta times theta. And I'm going to, I'm going to rewrite this as the probability of x I can always write as the probability of x given theta times the probability of theta integrated over theta. Right? I'm just doing this. Probability of A, probability of A over D times the probability of D integrated over D. It's the rule of total probability. So this is the probability of x1 given theta, probability of theta But now we should recognize this is the likelihood function. So this is the likelihood times the prior over the integral. In fact, this is a constant that doesn't depend on theta, because we're integrating out theta. So I can even write it this way. And so this is just a famous equation that the posterior distribution, the distribution for theta, given the x's, if I pretend theta is a random variable, is proportional to the likelihood times this prior. That's Bayes' theorem. Okay, so Bayes' theorem. Now why did I do that? Because now I have a distribution for theta, and I could extract an estimator from that distribution. I have this density function for theta. If you ask me now to make up a point estimator, well, I could take something like the mean of that distribution, or the median, or the mode, and so on. So we'll take the mean for now. So I'm going to say the Bayes estimator. This for now is just the mean. This is the mean. The mean of theta given x. In other words, it's theta times you could also take it to be the mode or the median. We'll just take the mean. And so that will be our definition of theta hat. And now comes the important part. You forget about the prior. You forget about the posterior. You forget about all that stuff. At the end, all I have is some function of the theta, an estimator. The fact that I went through this fantasy of pretending theta was a random variable and doing Bayes' theorem is irrelevant at this point. From the point of view of getting a Bayes estimator, it was just an algorithm to get an estimator. The final thing is just some estimator. We'll do some examples in a minute. And again, for those of you who are familiar with Bayesian inference, don't think about that yet. Okay, this is still just an algorithm for generating a point estimator. So the algorithm is make up a prior distribution of theta. I'm not sure how to do that yet. Multiply it by the likelihood. Treat that as a density function. And find the mean of that density function. So let's do some examples. A few minutes left. So let's do our Bernoulli. So how are we going to do this algorithm? Well, first of all, we need the likelihood, which is theta to the number of heads, and 1 minus theta, the number of tails. But now, to implement this algorithm, I have to somehow pick some probability density function for theta. So I'm going to choose, and I see there's a typo here in example 7. Let me correct that for you on the board. I'm going to somewhat arbitrarily choose the following density function for theta. This is my prior. And this is missing in the notes. So what is this thing? Well, first of all, the gammas are just a gamma function, so this is just numbers. These are just numbers. What's alpha and beta? They're also numbers that I've specified. So these are just fixed numbers, like 5 and 7, let's say, that I'm picking. The important part is this. This is this is some density on 0, 1. And the idea is that depending on which numbers alpha and beta I pick, I can get different shapes. So if alpha and beta are both 1, I get the uniform distribution. If alpha and beta were both 25, it would look something like this. It would be very sharply peaked down half. And by varying alpha and beta, I can get different shapes. So in other words, every different value of alpha and beta gives me a different prior and hence a different estimator. So the Bayes estimator is not really an estimator. There's an infinity of estimators. Every possible distribution for theta gives me a different Bayes estimator. And in this case, let's work out what the Bayes estimator is, I have to multiply the prior times the likelihood. So I'm going to say the posterior. And a lot of times we're pretty loose about, again, constants. The idea is that sometimes we can get away without keeping track of these constants. In fact, if I just toss these away and call it a constant proportionality, I can get away with that, because what really matters is this part times this part. I can see. Oh, did I tell? I forgot to say. This is called a beta. This is called a beta distribution, and it depends on these two numbers, alpha and beta. Kind of confusing. It's called beta distribution. There's beta there. But it's just some family of distributions. It's used a lot. All right. So. Now, when I multiply the likelihood times the power, what do I get? I get S plus alpha minus 1 minus theta, n minus S plus 1, n minus S. 1. All right. Oops. I forgot that. Notice what this looks like. It's theta to something minus 1, and it's 1 minus theta, something minus 1. That's exactly the same form as this. In other words, the posterior is also in this family. It's a beta distribution, but it's just that these numbers, alpha and beta, have changed. The alpha, the thing up here, has become an alpha plus x, and the beta has become beta plus number of tails. So what we conclude is that the posterior distribution is a beta distribution. But instead of having an alpha and beta, it's alpha plus s, and it's beta plus n. The effect of doing Bayes' theorem has been to take a particular distribution, a prior distribution, and convert it into a posterior distribution, and they're both in the same family of distributions. And now, luckily, we know a lot of things about beta distributions. So if I said to you, find the mean of this distribution, actually, how would you do that? How would you find the mean? Good exercise if you've never done it. Not hard. Just integrate it from 0 to 1, multiply it by theta. What you'll see is that the mean of this random, treating theta as a random variable, you'll see that the mean is this or this plus this. Again, if you've never done that, you should do it once. So let's apply that over here. The mean of this distribution is the Bayes estimator. So we know that the Bayes estimator is this over this plus this, which is therefore alpha plus beta plus n. And now we forget about all the Bayes' theorem and priors, and all that matters is I've just defined a new estimator. That's the estimator. That's a Bayes estimator. We shouldn't call it the Bayes estimator, I guess. We should probably call it a Bayes estimator. And if I manipulate this a little bit, it would be convenient to rewrite this as, I'm going to write this way, 1 minus theta where theta hat MLE is the MLE. Theta bar is alpha over beta, alpha over alpha plus beta. That was the mean of theta with respect to this prior distribution. And lambda is alpha plus beta over alpha plus beta plus n. So this is just a little bit of algebra, but it's showing us something important. In this particular example, our Bayes estimator is a convex combination of the maximum likelihood estimator and the mean of that prior distribution. And also, let's say, what happens to lambda as n goes to infinity? So suppose n was large. What happens to lambda? It goes to 0. So the Bayes estimator will be very close to the maximum likelihood estimator. Okay, so these mechanics that we're doing here are a good example of how we get a Bayes estimator. In practice, again, just like the MLE, it might not be so easy. People use Monte Carlo Markov chain method, there's all kinds of other methods to get these Bayes estimators. But conceptually, I hope it's pretty clear that it's fairly simple. We just pick some prior somehow, multiply by likelihood, get the posterior mean, that defines a new estimator. So from our point of view, we now have three algorithms, method of moments, MLE, Bayes estimator. In the end, though, we just get out, no matter which method we apply, we get out some estimator, which is really just remember, just some function. And we have not yet said why you should pick one or the other, they're just different estimators. Comparing them will be coming up. Let me see, are there any questions about that? Everyone's happy? All right. So we'll continue this then on Friday.